Hello everyone, I'm Paul and today we're solving problem 2528, maximize the minimum powered city. This is a reasonably hard one and here I will show you how to solve this step by step. We are given an integer array stations, so let's say that we are given this. And each element here corresponds to the number of power stations in the ith city. For example, here we have 1 power station, here we have 2, here we have 4. Now we are also given an integer r, which corresponds to the range for every power station in this array. So if r is 1 and we are standing here, we can provide energy to these 3 cities. The current city plus 1 city to the left and 1 to the right. Now if this was 2, we could provide energy to this city plus these 2 plus these 2. So all of this, okay? We are also given an integer k, which corresponds to the number of power stations that we need to add to some city in this array. Our job is down here. We need to return the maximum possible minimum power of any city after adding these k power stations. Let's forget about k for now and let's say that we are standing here at index 0. In this city, we have 1 power station and r is 1, so we are receiving energy from these 2 power stations also. So in total, we have energy from 3 power stations. Now we are here, given that r is 1, we need to sum these 3 values. 4 plus 2 is 6, plus 1 is 7. Next here, the total is 5 plus 4, 9, plus 1, 11. Here it's 9 and here it's 5. So if we keep this as it is, the minimum power of any city is 3. But our job is to get the maximum possible minimum power of any city after adding k stations. In this case, k is 2. So let's say that we add these 2 stations to city at index 1 here. So now we have 4 stations in total. The sum for index 0 is 1 plus 4, so here we have a 5, and from here the sum of 1, 4 and 4 is 9, so here we have a 9. Here we have 4 plus 4, 8, plus 5, 13, and the rest stays as it is. And the minimum value here is 5, so we just return 5. Because this is the maximum possible minimum power after adding these 2 stations somewhere here. And now the question is, how do we know where to put these k stations? Because here we use city at index 1, but if we use index 0, we get the same result. And if we put 1 power station here and another one here, we also get the same result. So instead of focusing on the perfect distribution, maybe we can try different minimum powers. Let's see what this means. Now let's say that we're trying a minimum power of 5. So this is the target. We are checking if for every city we have at least 5 power stations. And if we start here, we have a 3 and 3 is smaller than 5. So at this point, we will return false. Now the thing is that we can still add 2 power stations. This is the number of available power stations. So if we add these 2 power stations here, now this is 5. So this would be 3. And remember that if we change something at this index, we have a range that's 1, so we need to change everything within this range. So we need to change this number, and 3 plus 2 plus 4 is 6, 9. Now we are here and this is greater than 5. This is greater than 5, this is greater than 5, and this is equal to 5. So this is a valid target. Now if we try 6 for example and do the same, we start here and this is smaller than 6, so we add our 2 available power stations here. This is 3 and 3 plus 2 is 5, and this is still smaller than 6, so at this point we can return false, meaning this is not a valid target. So we can run a binary search from the smallest element in this array, meaning 0, to the sum of every element plus k. For this case, it's 14. And every time we take the midpoint and we check if this is a valid target. If it's not, we update the right pointer to mid -1, and if it's valid, we update left to mid. Here we know that the result is 5, so 7 is not valid. We update right to mid -1. Next, here we have left, right, and mid, so we try this target and we know that this is valid. We move left to mid to try higher targets. Next, here we have left, right, and mid. We try 5. We know that this is valid, so we move left to mid. Now here we have left, right, and the mid pointer is here because we are rounding up the mid pointer. So we try this target. It's not valid, so we update right to mid -1. Now here we have right and left, and given that right is smaller than left, we return left, meaning 5. Now we have one final problem here. We can't process this entire array from scratch every time because it's very inefficient. We need to think about something else. And for this we can use something called difference array. And in this array we are storing only the effect of every power station. Let's see what I mean. Let's say we have an empty array and we start from index 0. At this city we have only one power station and the range is 1. So we know that this power station will propagate one city. This means that at index 2 we no longer have this effect. So we can store here these two effects. We add this value at index 0 and subtract this at index 2, at index range +1. Okay, so at this point we have a -1. Now we are here, the range is 1, meaning this is the entire range. The left bound is at index minus range, meaning 0 here. So here we need to add the current value too. So this is now a 3. And the right bound is at the current index plus range +1, meaning at index 3. Okay. Now here we are out of bounds, so at this point we need to subtract this element. So here we put -2. Now we are here, the current range is this. And the left bound, meaning the index from which this effect starts to take place, is the current index minus range, meaning 1. So at this index, meaning here, we need to add this value. Here we put 4. And the right bound, meaning the first index from which this element has no effect, is the current index plus range +1, meaning 4. So at this index we need to subtract this. Here we put a -4. Next we are here. This is the current range. 3 minus 1 is 2. So at this index, meaning here, we need to add 5. So this is 4 now. And at 3 plus 1 plus 1, meaning here we will have one more index. Here we subtract 5, so we put -5. And here is the magic. Let's see what happens if we transform this into a prefix sum array. In case you don't know what a prefix sum array is, every element contains the sum of every element up to the corresponding index. First we have a 3, then 4 plus 3 is 7, then 7 plus 4 is 11, then 11 plus -2 is 9, 9 plus -4 is 5. And in case you didn't notice, this array is exactly the same as this. The thing is that we are building this difference array in big O of n time complexity, and this is how we reduce overall time complexity. Let's say that we are running our binary search. The current target is 5, so we are checking if 5 is valid. We iterate this from left to right, and as soon as we find a number that's smaller than the target, we add the corresponding power stations, if they are available, to the current index. So in this case we add 2 and the new value here is 5. And we will treat this as the left bound. And if this is the left bound, the right bound is here. This is the first index that's out of bounds in this range. The question is, how do we get this right bound? Well, we can take the current index 0 plus right times 2 plus 1. Sorry, this is range. Plus range times 2 plus 1. This is index 1, this is index 2, and this is index 3. 1 times 2 is 2 plus 1 is 3. This is the first index that's out of bounds. So at this point, we need to subtract these two power stations that we are adding here. So this is now minus 4. And as we are iterating this from left to right, we are also keeping track of the prefix sum up to every index. After adding these two power stations, the current prefix sum is 5. Next we are here. The current prefix sum is 5 plus 4, meaning 9. 9 is greater than the target, so we continue. We are here. 9 plus 4 is 13. 13 is greater than 5. Next we are here. 13 minus 4 is 9. 9 is greater than 5. Next we are here. 9 minus 4 is 5. And here we reach the end. We are just adding this element to build this difference array. And given that we reach the end successfully with every value greater or equal to the target, we know that this is a valid target. Now there's one last thing I would like to mention. Let's step back for a moment. The target is 5. We are iterating this from left to right. Initially we are at index 0. The current prefix sum is 3. And given that 3 is more than 5, we need to add power stations here. We have 2 available, so we add 2. And this is 5. And we are treating this as the left bound. This is the right bound. Now the question is, why is this the left bound? Well, because this is the first index from which the prefix sum is smaller than the target. And if we want to get a wider range, the widest range possible, we need to treat this as the left bound, okay? This is how we are sure that we are always taking the widest range. So with all of this in mind, let's go with the code and hopefully you will get the idea. First, n is the length of stations. We have a difference array, which is an array with 0 times n plus 1. And now we need to fill this. So for I in range n, difference at the current index minus range plus equal stations I, and difference at the current index plus range plus 1 minus equal stations I. Now it might be a case that this is out of range, so here we need to take the maximum between 0 and this. And similarly, it might be a case that this is also out of range. So here we can take the minimum between n and this. Okay. Now we can build our check function. This takes a target and we will have a copy of the difference array. We will call this DC for difference copy. This is a copy. We copy arrays like this in Python. Now the prefix sum is initially 0 and our number of available power stations is k. Now for I in range n, we add to the prefix sum DC at I, and now we are checking if the current prefix sum is smaller than the target. We need to add target minus prefix sum power stations. Okay. Now, if we don't have enough power stations available, we return false right away. So if add is greater than available, we just return false. Else, we add the power station. So prefix sum plus equal add, and we need to go to the DC at I plus the range times 2 plus 1 and subtract add. Okay, remember the approach. And here it might be a case that this is out of bounds, so we need to take the minimum between n and this. And finally, we need to subtract from available the amount of power stations that we are using, add. And if we reach the end of this loop and we never return false, we return true. And now we can run the binary search. Left is the minimum value in stations, right is the sum of stations plus k, and while left is smaller than right, mid is left plus right minus left divided by 2. And in this case, we need to round up this to get the right result. Remember, sometimes you round up this, sometimes you round it down. Now, here we can say if check mid is true, we update the left pointer to mid, else right is mid minus 1. Finally, we return left. So this is the entire code. I think this is right. Let's submit this and see if it works. Here I'm misspelling return, so let's fix this and try again. As you can see, this works and it's very efficient. Here the complexity is big O of n plus log some stations plus k times n. And space complexity is big O of n. So if you found this useful, drop a like, subscribe, and see you in the next one. Bye bye.